Oh, hi there. We're glad you're watching one of our virtual lunch presentations. We have a lot of good information that we've been accumulating over the past several years, and we invite you to look down just below here and hit the subscribe button, and the little bell will give you a reminder of when our next presentation is published here on the YouTube channel. Thanks for your support. Appreciate it. I'm really glad today, again, it's our friends at Kintronics that have supported us a little bit for our costs in bringing the presentation together. And they've been out there for 73 years now, Kintronic Labs, ever since the grandfather, Louis King, started it, and then Tom King, and now today we have this family affair continuing, and the third generation is in charge, and that's really a good thing to see. So they're a really nice family-oriented group, and you can have everything from a phaser constructed that will just get out there on site and tune up very quickly. You can see here they've got FM, STL, TV, telecom, filters, and such, engineering services. They have all sorts of towers and transmission lines. And their most recent has been to put a store up so you can order parts should you need them at any given time, day or night. And it's starting to fill up. A couple of weeks ago, there were just capacitors. Now we've got contactors, inductors, dehydrators, and more. And that is our friends at Kintronic Labs. But to our program today, I'm really pleased that from Dielectric, we have Nicole and Connor, and they're going to be giving us a discussion about the DA software that the FCC approved, where FM antennas can now be laid out in software rather than out of the test range, and also the in and outs of the new Pylon FM antenna. So I hope you guys have unmuted yourself, Connor and Nicole, and we'll turn it over to you.
Perfect. All right, I'm going to start. So Connor, if you want to stay muted, that's totally up to you.
All right.
I'm going to go ahead and share my screen, theoretically. All right, I've got our presentation here. So can everybody see?
Yes.
Okay, and is it just the presentation that popped up, or?
Next slide is also at the upper right corner.
Okay, interesting. Hang on just a second.
Is PowerPoint, try F5.
F5. That's still bringing this. I was hoping to switch this to one of my other monitors. Okay, so this is a little bit different, but I mean, you guys can still see the slides. So as long as everybody's okay with it, I will just proceed. I don't think I have any notes in here. So sorry about the format. So today, my name is Nicole Starrett, and today Connor and I will be presenting Changing the Landscape of FM Broadcast Antenna Technology. I'm going to start off by presenting the new FM Pylon antenna and how that compares to other antennas in the industry. And then Connor will take over with the FCC ruling change on simulation for FM pattern studies, and he'll go through where that stands, and also our artificial intelligence approach that we have developed for pattern optimization. So kind of to start off with a history lesson. It's been quite a while since any game-changing technology has been introduced into the FM broadcast antenna market. You go back to 1967, you have the BFC presented by Matisukola at NAB in his paper, Dual Polarization FM Broadcasting from a Single Antenna. And that antenna is the basis of our DCRC ring-style antenna today. Then in 1978, you have Don Hyman's IEEE paper, a new high power circularly polarized FM antenna, and that was the BFM, which has been adapted to our DCRM line of antennas. And around the same time, you also have the rototiller antenna that was developed, and these are all still very popular technologies that are used today. So what else is available? We talked about rings and tillers. We also have stub loops as well as panel antennas. What's common about these is they're all individual elements that use a feed system that could be pretty complex to unite them. So a while back, Dielectric started thinking about, well, what about pylon antennas in FM? How can we bring that technology to the FM world? I have a short video that I'm going to play.
Now, Dielectric is about to write a new chapter in FM radio's history of innovation. Antennas made with the pylon concept, fabricated as a cylinder, have been used with great success in the television industry, but only in the television industry. Dielectric engineers have now been able to apply the advantages of the pylon design to FM radio. The result is the new FM pylon antenna. The FM pylon antenna improves bandwidth without lowering the quality factor, which not only benefits your radio station, but your radio listeners. Dielectric has brought the principles we've been using in television antennas for decades to FM radio with the FM pylon antenna.
There we go. We have our little.
Now, Dielectric is about.
Sorry about that. All right, so continuing on. So what is so important about pylon antennas? What makes them special? Pylon antennas are an antenna term coined by RCA originally. They're a long, thin, round, top-mounted slotted coaxial antenna. They are typically smaller in size and less wind load than other types of broadcast antennas, panels, and whatnot. And the most important thing about pylon antennas is they're very simple. They have very few parts and connections, which make them very reliable. The vast majority of UHF and more recently VHF broadcast antennas, especially in the US, are these coaxial pylon designs. And this advertisement here is from 1966. It's one of my favorite old antenna advertisements, just a little bit of paint, and that's all you need because they're so reliable. However, pylon technology does have a disadvantage, and that is primarily a narrow bandwidth. In most applications, we'll use these antennas for a single channel. There are other applications with multiple channels. The natural bandwidth is around 1%. The percent bandwidth is defined by the equation on the slide at UHF for a VSWR of around 1 to 1 to 1, or 1.1 to 1. There we go. You can see that in the example on the slide here. We have a 100 megahertz span of a pylon antenna at channel 36. And you can see that at channel 36, that VSWR is nice under the 1.1 circle. But beyond that channel, it spreads out pretty quickly. So what are a couple of things that we can do to increase that inherent bandwidth? Well, there's a couple things. You can lower the Q, which I'm going to talk a little bit more about in a minute, and you can provide external phase cancellation in a feed system when you have multiple bays, and that cancellation will reduce the overall bandwidth of the antenna. Although I will mention that that cancellation is only applicable when you have multiple bays of an antenna. So if you're looking at a 4-bay single section FM pylon, as you can see on the screen there, we have to focus on lowering that Q. The expected bandwidth within an allowable VSWR specification is given by this equation. And what it boils down to is that Q and bandwidth are inversely proportional. So in order to increase bandwidth, you have to reduce Q. A standard pylon antenna Q is around 30 to 40, and we need 19% bandwidth for the full FM band. So in order to achieve that, you need to reduce your Q to between 5 and 10 for a max VSWR of 1.2 to 1. How can we do that? Well, based on the equation for the parallel resonant circuit, Q is directly related to the capacitance of an antenna. So if you can decrease the capacitance, you can also decrease your Q. If you look at a coax antenna versus a microstrip fed antenna, I'm not going to go through all of the math in the equations on the slide, but what it boils down to is the capacitance of the microstrip antenna works out to be about half the capacitance of the coaxial antenna. So the capacitance of a slot network can be greatly reduced by changing the coaxial inner to a microstrip. And like I said, using a microstrip fed slot cuts the Q in half, which effectively doubles your bandwidth. What else can we do to increase this bandwidth? This brings us to Babinet's principle, which was originally a principle in optics, but H.G. Booker related this principle to antenna theory in the 1940s. And what it boils down to is a slot is a complementary or a dual of a dipole. So if you place a slot and a dipole in the same circuit, you get an inverse response, which lowers your Q. We've done extensive testing on these parasitic dipole elements here at Dielectric, and those tests have shown that your Q value is cut in half, which again doubles your operating bandwidth. The great thing about this parasitic element is that this technique also provides circular polarization for the antenna. So that parasitic dipole couples the horizontal polarized energy emanating from the slot and re-radiates it into the vertical plane. So if you look at a single section FM pylon antenna, this is the testing we did on our 25-foot trestle. This testing confirms that using the methods I mentioned before to reduce the Q allows the VSWR performance to be less than a 1.2 to 1 for the full FM band and that plot is shown on the slide there. One thing we have to consider with this antenna is the polarization ratio stability across the band. We started out with a very simple floating dipole, which is pretty standard. We've used a floating dipole element on many VHF and UHF antennas. However, this design does have a limited bandwidth. Widening the dipole can help, but you may have to change the geometry to achieve stability of the HV ratio across the band. If you look at the azimuth patterns on the slide, you have H pole in blue and V pole in red. At 98 megahertz, everything's hunky-dory. You have your nice circular polarization, but when you look at the ends at 88 and 108, that V pole drops down about 10 dB, which means that this geometry is not acceptable for full band FM performance, and we need to change that geometry to expand on the dipole concept. This is where our double dipole parasitic element comes in, and adding a second dipole and changing the geometry applies log periodic principles to the radiation. So each dipole will resonate at a different part of the band. And as you can see in our azimuth patterns, this really helps the circularity at the ends of the band. And then in the middle of the band, it's reduced slightly, but only about 2.8 dB. This variation is pretty comparable to today's broadband single element designs. And if you compare it to a single parasitic, it's a heck of a lot better. So you no longer have that 10 dB drop at your ends. So as with any research and development project, we have learned a lot during this project. One of those things is when you switch to a dual dipole design, due to you no longer have the duality of the dipole and the slot relationship within the same circuit, your bandwidth is compromised. So the next steps on that project have been to explore different options to improve that bandwidth. There are a few ways you can do this. One of which is applying a phase rotation between bays for a 4-round or 3-round configuration. When you have multiple bays vertically, you can also add phase between the bays for cancellation, as we talked about in a few slides ago, and adjusting the internal components to just improve the overall bandwidth of the antenna. Another thing that we have been working to improve is the manufacturability of the antenna. Originally, we planned to have a rounded extrusion, as seen on the left there. But we found economically that may not be the best way to go. So recently we've developed a folded box design. So you start with a flat plate, you do all your machining on the flat plate, then the box is folded up like origami. It's a much simpler and more economical way to do things. And as this project continues, we continue to explore other ways to simplify the design. So let's talk about our patterns in free space and what happens when you put them on a tower. Your FM Pylon's free space pattern is not an omni, as you've probably noticed on our previous slides. It's an omnioid, and therefore your H-pole and V-pole are not quite congruent. But is this a problem? Not necessarily. If you compare an FM Pylon free space pattern to a free space DCRM or other ring style, yeah, they're pretty different. You have your full perfect circles for your DCRM in free space, but you have to mount an antenna, you have to feed an antenna. They're never just in free space. So once you add a feed line, your pattern starts to approach that of the FM Pylon antenna. Similarly, when you put an FM Pylon and a DCRM on the same size tower, pointed in the same direction, you have a similar pattern shaping between the two. So let's talk about the flexibility of these patterns. I know a lot of people like to use panel antennas because, well, you can point them in different directions and make your pattern pretty flexible. Well, these are all things that the FM Pylon can do as well. It's not limited to a single bay. You can use it as an array in many different combinations. You can get your omnis, your peanut patterns, your cardioids, your skulls. You can see the FCC Protect on the right there. You can modify the layout of the FM Pylon antenna to achieve those different patterns as well to meet your FCC Protects. There's also a lot of flexibility in the elevation pattern for the antenna. And this comes from a combination of different bays and the change in amplitude and phase between those bays. So each section is fed with an external feed line from a power divider, and you can change your number of sections and your phasing to each bay to change your gain, your beam tilt, your null structure. One thing I really want to hone in on here is the simplicity and the reliability of these antennas. Pylon antennas have always been known for their simplicity. We talked about that at the beginning of the presentation. Fewer parts is more reliable. I have an equation here for failure rate, and I'm not going to go through everything, but it boils down to failure rate is directly proportional to the number of parts you have on that antenna. So if you can decrease your number of parts, you're getting a more reliable product. Your FM Pylon antenna has 60 less parts than an equivalent ring style and 90% less parts than an equivalent panel antenna, which makes the FM Pylon much more reliable than any equivalent FM broadcast antenna on the market today. Another thing to consider is power and voltage handling for this antenna. The voltage safety factor for an antenna system under combined multi-station operation is defined by this equation on the slide, which is from John Shadler's NAB 2015 paper. At Dielectric, we use a recommended voltage safety factor of 5:1, and this was defined again in John Shadler's paper in 2018. This is based on extensive high-pot testing. And for this example, we're going to assume that each station runs at -14 dBc IBOC. If you look at the table I have here, we have the average power in kilowatts per station, with that IBOC assumption, and assuming our 5:1 voltage safety factor. And you can see if you're comparing it to or if you're creating a top mount Omni master FM application with 4 sections around, you can accommodate 6 stations at 20 kilowatts each with the same assumption of -14 dBc IBOC and 5:1 voltage safety factor. So you really don't hit any limits, any voltage limits on this antenna until you start combining 7 stations. The last thing I have to mention is the mechanical wind load comparison for this antenna. This is all done in G-code, just to keep everything the same. And we compared a 4-bay pylon antenna to an 8-bay half-wave spaced ring, which you need the half-wave spaced and additional bays to improve the bandwidth of the antenna. In this case, a pylon actually has more wind load than a ring style by about 18%, but it's pretty comparable. However, when you add radomes to that ring style antenna, your pylon has 22% less wind load than the same with ring style. Similarly, if you compare it to a panel antenna, you have a 4-bay top mount Omni pylon versus a 3-around CBR, your pylon has way less wind load by about 20%, and even more so when you add ice, which makes sense if you think about it, because there are so many nooks and crannies on a panel antenna that ice sticks in there and adds a lot of wind load. So that is all I have for the FM pylon antenna. I'm going to stop sharing my screen now, and Connor can take over. But before he does, there we go, to get back to the presentation. Before he does anybody have any questions about what I presented so far, or any thoughts or anything like that?
Sure. You mentioned wind loading and icing. How does the wind icing affect the antenna bandwidth? Because I don't know if you're familiar with Western Maine, but I have a site with a 10-bay Shively antenna that can get 6 to 8 inches thick icing sometimes. And I've had pretty significant foldback. Sure.
No, that's a completely reasonable question. I don't have the exact values in front of me for how it affects the VSWR. As we all know, ice affects antennas and the VSWR, but with the pylon design and the radome around the whole thing, it sheds ice very similarly to a standard pylon, so icing is less of an issue than with a typical ring style or panel antenna.
On a conventional antenna, if you have a damaged bay section, you can have it removed and still continue to operate. What would you do with a partial damage on your system, your new system?
That's a great question. Since the technology is so different, you can't simply remove an antenna bay. But with the simplified layout and much fewer parts than typical ring styles or panel antennas, you have an antenna that's typically much more reliable. So if it does go down, the parts are readily available here, and it can be repaired pretty simply.
But you'd still be able to operate at reduced power?
It depends on the damage, I suppose. I think it would have to be a case-by-case basis, but that's not unreasonable.
Nicole, what?
I note that when you refer to sections, you're actually referring to 4 slots per section.
Correct. We have a 4 slot or a 4-bay configuration. We also have a 2-bay configuration.
Okay, so should we, assume that the gain of a 4-slot section is pretty much equivalent to a gain of a 4-bay standard FM fully spaced?
Yes, they would be pretty equivalent.
Okay, thanks.
Nicole, one of the questions we have in the chat room is how many of these have been installed so far?
That is a fantastic question. I know we've had a lot of interest, but I don't know if I don't think we have any installed in the field yet. It's still developing technology, but we've certainly been proposing a lot of them and had a lot of interest. So we'll cross that bridge when we get to it.
Still brand new. Another question would be, how would the pricing, not that we're asking you for specific numbers here, but how would the cost of a pylon compare, let's say, with a panel or a ring antenna?
So I don't have the exact costing in front of me or even a percentage. That's a wonderful question, but I can tell you that with fewer parts and a more simple design, your cost should be at least equivalent, if not less expensive, for a pylon antenna. But I would have to check with our marketing and sales department to have all of those numbers.
No, I was not trying to put you on the spot there,
sure.
But when you said fewer parts and easier construction, then someone who's considering an antenna should certainly pay attention to this pylon as a less expensive way of getting the same thing done and accomplishing the task.
Absolutely, and a more reliable way.
How about beam tilt and null fill and pattern optimization? How is that achieved?
So that's a wonderful question. As far as elevation pattern goes, we have multiple bays that we can stack on top of each other. So you can have a combination of 2 bays, you can have a combination of 4 bays. And as we change the amplitude and phase between those bays, or between those sections, it will change your beam tilt and your null fill. So it's very customizable. As far as azimuth pattern goes, from my slides, a single section is that nice omnioid B pattern. But when you combine those into a 4-round or a 3-round configuration, you get your omnis or peanuts, and you can change the phase and amplitude relationship between them to shift the radiation in different directions.
But you would have a way of, for instance, in the old days, they used to put the antenna out in a field, 1 bay with an actual mock section of the tower and use it as a receive antenna. And then they had like a little train that went around the tower to optimize pattern off of that particular tower.
Right, right. So that is all done in our HFSS software, which Connor's actually going to talk about in a few minutes. So we are able to simulate the effect of different phases and amplitudes and the effect on the azimuth pattern in real time.
William would also like to know, when you say mount, say 2 sections on top of each other, they need to be fed from an external line up the side?
Yes, that is correct. So they would be fed with each individually with a feed line connected to a power divider. And then, yes, to get more omni, you would put 3 or 4 around in a mast configuration. Yes.
Sort of like panels.
Yeah, very much like panels, but a little simpler.
Would that give you the option then, if one of the sections were to be damaged, you could disconnect it and tap something off or put a dummy cap on it or something to continue to operate while you're getting that section repaired?
I think that's reasonable. It would depend on your configuration and what the damage was, and shifting the input to whatever sections you have remaining, but that's probably something that could be done. So,
you have time for a philosophical question?
Absolutely.
So the FCC is slowly easing into the 20th century, and so the swap from having little model trains running around a track around the antenna to a computer is changing that part of it. Some of what I kind of see as arbitrary, prohibitions about the rates of change of patterns may have been stuff that was left over from when you had to bend the antenna elements with your bare hands and then check them.
Right.
Is something more? Do you think the commission at some stage will soften some of those rules, and will your new antenna design accommodate quicker pattern?
Sure.
Power changes.
Well, I can't speak for the FCC or any government organization, but honestly, I would love to see some modernization there. I can tell you that the software that we use, it's an ANSYS product called HFSS and also OptiSlang, which Connor's going to talk about, is completely customizable. So it allows us to do a lot more than you could do with your bare hands in the old days.
Is your circular polarization true circular, or is it more like horizontal and vertical?
That's a wonderful question. It is true circular at a certain point in the band, but not necessarily all across the band, if that answers your question. So
this is John Shadler from Dielectric. Maybe I can help fill in some of the gaps in the questions here, if you don't mind.
Sure.
So Ken, to answer your question, we do pay attention to the phase between the horizontal and vertical components, so that it is truly circular. In other words, it has a good axial ratio. Even though there's no company that specifies axial ratio, we pay attention to it to make sure that, in between horizontal and vertical, that you actually do have field. Just a few more comments. I've been listening to all the great questions. As far as the icing goes, the fact that the antenna itself has a low Q, which, Q is how resonant the antenna is. The lower the Q, the less effect that you actually have from icing. In other words, your resonance doesn't shift due to the icing. No antenna is immune to ice, but it is pretty numb and unsensitive to to icing. The other question I heard was about damage. Keep in mind that inherently a pylon is less susceptible to damage because we don't have external feed lines and power dividers and things hanging out there that can get damaged by ice falling. I think somebody asked how many we have in the field. We are still looking for our first victim, if you will. But what I will say is this: the concept of a microstrip fed slot with a parasitic dipole we use on our TLS-V style antennas, which is high band V. And during repack, we actually shipped a little over 200 of those. So the technology is not new to us. It's really just a scaled version of our TLS-V. As far as pricing goes, our goal here is to become competitive with high power ring styles. So, we're trying to get the pricing in the range of a 4 to an 8 bay ring style antenna. And, hopefully the fact that it comes along with easier installation, since it's only one piece, reliability, because you don't have the, external feed lines and power dividers and all that. And the fact that it can probably be installed much quicker than individual elements that have to go up the tower, that would offset any small difference. So hopefully that helps with some of the questions you guys had.
Appreciate that, John. Thank you very much. Does anyone else have a question about the pylon? I know Connor is just chafing at the bit here, ready to roll.
I'll just add one quick question about the physical size of this pylon. The one that you got in the presentation, this is an all-band pylon, correct? In other words, or is it centered on a particular frequency? In other words, does the physical size or length of the pylon change, or is it just pretty much fixed?
It does not. It's a fixed size, and it's a broadband concept. So the skeleton of the antenna is the same.
And therefore also the dead weight and things of that nature pretty much stay the same.
Correct. Yep. All right, so I will hand it over to Connor. And if there are any other questions that pop up, we can answer them at the end.
I'll start sharing my screen then.
There it is.
Okay, so I'm going to be talking about how we are going about the AI approach to FM pattern studies, directional FM pattern studies. So I'm going to start by talking about the FCC ruling as of now. In June 2021, we filed the proposed rulemaking to the FCC to allow us to use computer simulation for directional FM. And then in November of 2021, we had a unanimous vote by the FCC to move forward with the notice of proposed rulemaking. And we had strong support from them. They reduced the public comment period from 90 days to 30 with a 2-week extension for Christmas. And then the public comments were also very much in favor, with 18 in favor and only 1 opposed. So after that, the NPRM was passed on a final vote. So it is going through. And then the next day it was filed to the register. And now we're just waiting for the Office of Management and Budget to approve it. So we expect this to go through and to be doing simulated patterns sometime around September. So how we're using simulation for FM directional studies. The petition was based on a lot of benefits that this has over traditional range measurements. One of many being the cost advantage. It's a lot cheaper doing it in simulation than it is to maintain an FM range with all the models and towers and things like that. It's also in a reflection-free environment, so there's no error for reflection, or you don't have to worry about that in the simulation space. Mechanical tolerancing is much better. Simulations we can set to exact lengths given tower specifications and things like that. There's less human error. Being with range measurements, you have to measure it with a ruler and then scale it from there, and there can be error there. But in the simulation space, we can get exact measurements and know exactly where things need to go. There's also complete optimization for these patterns. Because of the software we use, we can get a much better pattern. And also using that software, our time constraints are much better. Lead time goes down because of the software that we use, and I'll go into that later. Also, this is kind of standardizing the way people can do patterns because every range is different, right? So this way in simulation they can all be the same, and it'll be very reproducible, and the quality of these patterns should be better than the range. So in computer simulation, the process kind of goes like this. It starts with us grabbing a tower model and the antenna that the customer wants. We run a start pattern given the FCC Protect, which you can see in green, and the horizontal pattern is in blue, and the vertical pattern is in red. And based on that, we have to adjust the bay to keep it in the Protect, and then we put on parasitics to try and get more coverage, and then maybe a vertical parasitic too. And after all that, we check that it complies with the FCC. And then we send it to the customer, which they usually critique it, and we have to start the whole process over again. But with our artificial intelligence optimizer, which we are calling AIO, this whole process can be automated, which greatly improves lead time and how much time we have to spend on these patterns. So this is how we're kind of going about it with the AI optimization. We're using software called OptiSlang, which is another ANSYS product. And they have many different theories and math algorithms you can use, but we decided to stick with the particle swarm optimization theory, which seems to be working very well for these patterns. And it's basically based on how bees will swarm to different points, and it's basically swarming to the point of best design, which is what we're doing. So the process, we solve it in HFSS. We export that data to OptiSlang. OptiSlang will run, it can run 200, 300 iterations, however many you want. And it reads all the data and makes smart decisions based on that to find the best design with the parasitics that it has. So how this improves our lead time. Before in the range, we would have to take about maybe 4 hours to set up the model in the tower, and we could get maybe one pattern every 20 minutes, and this was usually a week to get a single pattern. So you have a lead time of 5 days where you only get maybe 120 iterations of that pattern, and it takes about 80 hours for the techs to run these patterns. But with computer sim and AIO, it's about an hour setup time and 20 to 30 hours cycle time. So this is, without a person even being there, it can run overnight, in the morning, it doesn't matter. It'll do it on its own, and it can only take maybe 20 hours. And the results are better. You get 300 to 400 iterations you choose from. It's optimized. So the lead time is maybe 1 to 2 days, which is much quicker with less tech hours. So this is an example that we did. On the top, you can see the start and end pattern, the protecting green, the horizontal in blue, and the vertical polarization in red. And you can see that it stays within the protect and fills out. I think in this example, it was about 87%, and it still met all FCC rules. So this was after running 310 iterations with OptiSlang, And you can see on the far right, each black dot is a design, and the z-axis is the coverage that we're trying to get to maximize, with a few different variables like the parasitic length and the bay angle. And you can see that they're kind of swarming into a point where where the best design is. So you can see how it's optimizing. And the GIF is showing through the iterations how the pattern is changing to get the best one. So the first 100 are very erratic. These are just random designs, and it's the bees looking for a direction, right? It's they're trying to fill the design space and figure out what does what. And then as it goes on, the last 50 iterations are very small changes because it's honed in. The bees are swarmed into that point where the best design is, and that's when it's optimized. And this one here took 21 hours to run, which is much quicker than in the range. So to conclude what we already talked about with the Pylon, the unique design compared to other FM antennas, it utilizes all the advantages of Pylon technology from UHF and VHF. The low wind load, it's very simple, less parts, which increases reliability, and the azimuth and elevation pattern flexibility with it. It's also broadband, and we're working towards a full band operation. And it's cost-effective and simple alternative to FM element arrays and panel-style antennas. And I talked about how we're preparing for the SEC ruling that's going to be happening in September, how we're using AIO to automate the whole process and optimize patterns, and how this adds a new level of efficiency and accuracy to pattern studies. So that's everything. If we want to have questions or talk about the process.
Have you done this in real life for anybody, and what were their results if you have?
What do you mean real life? Like, have we done this for a pattern right now?
That is out in the field operating.
I don't know if any are operating right now. I've done a few for translators and things. We can't do it right now because the ruling hasn't gone through yet, but I've done it for a few translators, and it's gone very good, and the customers are usually pretty happy with it. I don't know any callers on the top of my head, but I believe we do have some translators out there that I've done this on.
Going back to the Pylon for a moment, are these aimed at high power installations? Would medium power be installation of something like this be cost effective?
Oh, that is a great question. John, if you want to jump in again, feel free, because I don't know all the costing details, but yeah. I think it would depend on the application.
Yeah. So it is kind of interesting. We first started talking about this internally. We thought the killer app here would have been the broadband capability. It turns out that with all of our discussions with individuals who are interested in this, that the killer app is actually the fact that it's a Pylon. It seems like everybody's familiar with Pylon antennas and their advantages, and certainly their simplicity, and them lasting 50 years in the field. So most of the inquiries that we've been getting have been coming from single frequency FM stations. So that's one of the reasons why we're focusing on manufacturability, and trying to bring the pricing into the range of a standard ring style. So I feel that it's probably going to be more expensive than a low or a medium power ring style, but it's going to be very comparable to a high power ring style.
I agree. I think that the immediate interest when I saw the Pylon, I said, okay, well, so it's a big broadband thing, and I can get away with having panels all around, like a 12 around, a 4 around, and, get rid of all those individual panels and all that spaghetti interconnects and things like that. So, and it's broadband, so that appeals to a lot of consolidation. But it also has wide appeal, I think, to our individual users that may have tower loading issues or something of that nature, that may need the advantage of the Pylon.
Absolutely, with the reduced wind loading in most cases compared to other similar antennas, ring styles, or panels, it will definitely help with tower constraints.
One of the questions that might arise here, Connor, you mentioned that this particular pattern took about 20 hours. This is not something that we're going to do on our home computers anytime soon.
No, no, we have some pretty beefy computers here that can run a lot of different sims. I usually am running like three in parallel at a time to get the sim time down. But yeah, we have some pretty big stuff here.
You wouldn't, Barry, you wouldn't want to pay the license cost for that HFSS.
That's
So
very
there's
expensive.
no phone app.
No.
So you have a 1 to 2 day design, and then the output of that design gets plugged into a laser cutter and a machine bender, and in a week you've got an antenna shipped, right?
It's not exactly as quick, but yeah, pretty much. I draw a sketch of it and then it gets sent out.
Hey, Connor, I live in Maine. I'd love to see one being built. How do I set that up with one of you guys? Go through sales?
I'd assume John. I don't know. John Shaler would want to
I
set
mean,
that up.
I've been through the plant, you know, I've picked up stuff there before and everything, but this is a fascinating technology and I'd really like to see one being built just because I'm so close.
Yeah, I don't mind showing you, but yeah, it's up to John.
Yeah, sure.
And you can reach out to one of us. You can reach out to Kim Savage. You can reach out to customer service. You know, we'll make that work.
Thanks. Yeah, I'd love to.
Yep, Tim, just come visit us and we'll do a little demonstration for you. It's
Cool.
it is pretty neat.
Yeah, it really, it's fascinating technology, and you know, I think it's the way we have to go. You know, with antenna design and construction these days, especially with sites being, you know, what they are.
So it appears that with the antenna modeling system, that a lot of the time that it takes is actually in the computer simulation time, with only about 1 hour of active involvement from the technician. So that seems to imply that in the future, as you either scale it out to, say, AWS or even just having more powerful computers and processors on your end, that number, the biggest limiting factor is the compute, which is pretty much the only thing that is guaranteed to get better and better over time. So
That's true. Yeah, that's very true. Right now, we're actually limited by how many licenses we have. So you also need more licenses too. But if I could run, 10 in parallel, it'd be 10 times quicker. So it is definitely limited by that.
Apply your qubit computer to it.
Yeah.
Or buy a used Cray. Too bad that Glenn Clark is no longer with us.
I don't know if you hook up with any 18-year-old kid who's got a gaming computer. I mean, those things are beasts. I mean, come on, how many Xeon processors do those things have in them? Get it. Don't you guys know some gaming guys? Get their computers, man.
That's an interesting way of looking at it, isn't it?
Yeah, my biggest computer so far is only got 128 Xeon cores, so that's a limit.
And I need that computer.
Do we have any other
I'll
questions?
just add a little bit more if I'm on. Okay, that the software itself I'm familiar with. I've used it extensively, not personally, but interacted with my antenna designers in London for the project on top of World Trade Center with VHF television. We then went out and that was a big panel antenna wrapped around 4 bays and things of that nature. But we then went out and field measured it, and we were very, very pleased with the results matching what the pattern study, what London was telling me to expect. And there it was.
Yeah, it is very accurate. It's as accurate as the customer giving us the tower info. So that's what it comes down to. It is more accurate than a range, I think.
So does anyone else have a question for our friends here, Nicole or Connor or John? Well, I certainly want to thank all three of you for being with us today. Appreciate it. It was very interesting to not only see what you've been doing with the Pylon and the software. I like this bees concept, and we appreciate that very much. And as you get these into the field, I certainly would like to invite you back, and perhaps we could do a short presentation or report on how they work.
Sure. Yeah, we'd be happy to do that.
Great presentation.
Thanks, Dan.
Thanks.